linear approximation and differentials. Very nice, interesting topic, which explains you how coding, so if you're a computer scientist, you will love this, how coding saved, people, and at some point revolutionized mathematics into applied mathematics, into computational mathematics. And one of those basic ideas which were implemented in coding, Java, C++, Python, R, were using a derivative. Using this stupid tangent line, we're forcing you to learn so hard because you will use it. Many people are paid at their jobs to do that. And the idea is, you don't have to make this picture, but the idea is why at the cusp there's no derivative. Because derivative exists if you can zoom in. So here's a function with some kind of shape, nice smooth shape. And here's a tangent line at P. I'm using zooming in property of the screen or maybe your device. Zoom it in. You see it becomes flatter. Now it's not that curve anymore. I'm zooming in more. Now it's really, really flat. So at some point it becomes so flat that the tangent line almost matches with the curve you have. And that's a cool property of the tangent line. So it seems like if you zoom in close enough, we can use tangent line as approximation of the behavior of the function. So imagine if the function is crazy and very complicated, arc sine of log over trigonometric functions times over quotient rule, and then I'm like, I'll just find a tangent line, which is a line. It's mx plus b, how hard it can be, and use that instead with some kind of error, and these empty gaps will be little error. And if I don't go too far from P, the approximation can be very good. So that's a cool idea. Instead of finding whatever this function is at P, I will use the tangent line at P. Over here, or over here, and over here. And, I just know don't go too far. Then the approximation is good. But if you have a cusp, that's impossible to do. Here's a cusp, or a sharp corner. Derivative does not exist here, even though the function is continuous. Why? I'm zooming in, it's still a cusp. I'm zooming in, it's still super annoying, and it doesn't become flat. So that's why I cannot use derivative here. Should I use this tangent line, this tangent line, this tangent line, this tangent line, or this tangent line, or this tangent line? There are infinitely many tangent lines here. None of them will represent this perfect approximation. So the definition of derivative does not work here. And that's why we say there's no derivative at cusp. And the idea is, shown over here in this animation. It's exactly what I just said. There's a function, it's smooth and nice. And we're zooming in, keep zooming. The more you zoom in, the more flat it becomes. And then the more you zoom in, the more it behaves like a line. So that's very cool. What if we can approximate all functions like this? Regardless whatever you model, you can approximate with lines and then work with lines instead of the curves. That's a big deal because, it's convenient to work with a square versus with sine, which is keep escalating and moving everywhere. And flat surfaces are just convenient to find maximum of the table. That's easy, but versus find the maximum of the deep mountain underneath of the ocean, that's complicated. So it'd be nice to have some kind of tool like that. And that tool is called tangent line, which we know from school. So very nice link into a movie, Hidden Figures. I always mention this example. Did you watch Hidden Figures? Did you like it? It's an amazing movie. It's awesome part of the American history. I do not know, by the way, the end of the movie because I don't know the history of American astronauts. So for me, it was very fascinating to know if he's going to die or not. But for you to know, they used this method, and that's how they sent the first American into the space. The method called in the movie called Euler's method, which is still a decent method. People are still using it. And it's true. They did not make it up. You can check this link, and Wikipedia shows you. And this method was used for Mercury Atlas 6 mission to send astronaut John Glenn to the orbit of Earth. And this is how it looks like. This is exactly the model they had to build without computers. Do you remember how horrible the computers were at that time? And they were calculating all the super slow. But it's exactly what she did. This lady there Catherine, she offered to use this Euler's method because they could not find where the shuttle will land when it's going to return. And it's nice if it's not going to land on some mountain and break, right? So they wanted to make it sure it will land on the ocean. But the earth is keep spinning, the wind is keep working, gravitational forces keep working. It's hard to do it precisely, so we still use approximation till now. And she said, okay, we're setting it up and then it goes down. Can we predict this point? Or what if something goes wrong? Then the point shifts. So using the orbit of the earth and the speed of the rotation, gravitational forces, she offered to use Euler's method. It's old, and people still use it right now. It still works well. And she said, you know what? We cannot exactly know what's happening with this move of the shuttle. Let's use tangent line and approximate this instead of this, and then take into account the error, plus minus couple kilometers. And it worked well, and it's exactly what happened. It's here. This is visualization of the Euler's method. Look at the beginning. At the beginning, start the first tangent line, second tangent line, third tangent line. And instead of walking on the curve, we walk on a tangent line. And it gives you some kind of error, and it works well. You can even know, there's even a study how to minimize that error. And we're going to teach you how to calculate this error. And you code all of this. You code it in Python, C++, Java, whatever you like to use. They all have packages for Euler's method already included there. And you give the curve, and it uses tangent lines to approximate the solution, and you can look into the future. Think about that. Derivative shows you the future, because the shuttle was not even in the space, and they already figured out where it's gonna land. Think about how fascinating this idea. The tangent line goes up and beyond to the future, and if you don't go too far, you can use it to approximate some kind of future moment. And then say, in the future, the shuttle will be at that location. And it's still used. So that's a cool idea why we're teaching all of this. There will be a class where you will be learning all of this in details. For now, we're just gonna give you the definition and go through some examples. Let's do it. What do we know? We know y minus y naught equals m of x times x minus x naught. M is a slope. x0, y0 is a given point. We know that. But also, why are we writing it y? Maybe it's called g, like gravitation, or f, or m, whatever. So let's call it f. Instead of y, I'm just calling it f. F of x and then f of y naught, but let's call it a. So a will be my input. A is basically x naught. It's just nice to call it. A is some kind of point, given x coordinate of the point. Then, if you have this, we can solve for f of x. Solve for this. Solve for f of x. F of x is exactly f of a plus m x minus a. I did not do anything. I just solved for x. And that's exactly what approximation means. Well, for now it's equal sign. But the idea is I want to find this. F of x is my output, where the astronaut will be in 45 days. Using whatever I'm having right now. I know right now the rocket is at this location. A slope, that's how steep or the rate of the rocket flying in the space. X minus the position I have. Make sense? So that's interesting. With the given data, can you predict the future? Yes, using tangent line and derivatives. And then we call this m. What is m? M can be called, or I would do like this. Right now it's an equal sign. But the moment I change m, f of x is approximately f of a plus f prime of a x minus a. If I take derivative in general at a, then this is approximation, and this approximation is called L. That's what we're gonna call from now on. And we're gonna do on the right hand side. L. linear approximation, that's the definition. Linear approximation, that's by capital L. And this leads to the definition. Linear approximation of f at A. We say f is differentiable. What does it mean to be differentiable? Who remembers? No. Well, continuous, that's if f is continuous. But a differentiable, I know what you mean. If function is differentiable, it means continuous. So good job. But the idea of having this phrase, what does it mean? That f is differentiable on the interval. Who knows? Who remembers?
No.
Kind of. Huh?
There's no
Cusps?
Yeah.
Yes, but in general, I want just to hear it has derivative. That's you guys are overthinking. I'm just asking you, do you remember differentiable means it has derivative everywhere on that interval I? So you're right, and you're right. Many of you are right. It means that this trajectory of the shuttle, for example, is going to the space. It will go smoothly, at least on the interval I. It goes up, I guess, drops off this heavy piece of it, goes up, drops off one more piece, going up, then slows down, and it becomes a smooth curve. So on I can claim that the function that represents this trajectory has derivatives everywhere. Then approximation of f has a linear approximation, and this is called L of x. To find the linear approximation, find f of a, find derivative at a, and find this difference x minus a. And that's exactly what we do to find the linear approximation for functions. Now, yeah?
So the slope on the second equation, there's no slope because you don't know the slope?
So this, yeah, we have to find it. That's a very good point you just mentioned. That's why we say the trajectory is given, that's distance. And I find the velocity, and that's the derivative, right? So we don't give it to you. So you have to differentiate using chain rule or whatever we need, logarithmic differentiation sometimes. But then I said, at this point, plug it in, and you can find approximation and look into the future if you was able to differentiate. And that's a drawback of the methods. It's really cool if you notice it. Not all functions are easy to differentiate, right? So new methods popped out after that. Euler offered this method, and when computers show up, this was implemented really well because it was easy to calculate. But then other methods avoid finding derivative at all, and they work different way. If you take classes in numerical mathematics and all of those methods, numerical methods, they will show you really cool stuff there. So did you hear I said that it's not exact, right? So that means you will have an error. And that's the first time we introduced you to this idea of the error. Whatever you did, your work might be useless if error is huge. Makes sense? And it's really important. Not all scientists admit that whatever they're presenting at the conference right now, being super proud of publications, is bullshit. And then we sit in the audience and we're like, excuse me, what's your error? And they don't want to admit that the error is like 75%. Then who cares what your results are? You know, I can claim we solved the cancer problem with 75% error, you know, like who cares? So that's important actually to know that whatever you're doing should be justified and your error should be small enough. And then small enough, it depends on the problem. Small enough 0.01 error, or small enough 0.0001, and so on. So the exact error can be found by taking the exact solution minus approximate solution. Makes sense? And then if it's negative, you don't use negative sign. That's why we do absolute value. In this book we're working with, they introduced percent error. Percent error is take exact minus approximate, find the ratio with exact, and then multiply by 100%. And that gives like the 75% idea that, okay, there's an error of my results, and it is 1.7%. And it sounds like not a lot for many problems, but for some problems, that's too much. So we will be asking you to find this. The percent error actually is not very popular, but I personally liked it that they introduced this. Let's do it. Let me show you a nice example, and let's do all of these now. Example, without using a calculator. Okay, you forgot your calculator on the exam. And then I ask you to calculate sine of 0.17 in radians. Can you do it? Using linear approximation? Yes, you can. Because it will be very simple, actually. I will show you how it works. And that's the whole point. Of course, it sounds a little bit dumb. Why we cannot just use calculator for sine of 0.17? But it's a simple example to do in class. When you do research, it's really complicated. So, and you can still avoid using calculator to do it because it's exactly what they did, what they showed in the Hidden Figures movie. They did it without computers. Think about that. Making calculations in row by row by row in a huge table, and they calculate where the shuttle with a living person in it will go into the space and then go back using this method. How fascinating is that? So the idea is we're going to first calculate the linear approximation to find these A, B, and C. And we're going to calculate the error for each case. So first solution. Let's find linear approximation. And then we know we're working with the function y equals sine x. Find, okay, let's do it this way. Find linear approximation for y equals sine x. Find linear approximation for y equals sine x. The formula says L of x is f at a plus f prime at a times x minus a. So we're gonna use those steps, but first, did I say where? First, I will use some point close to 0.17, negative 0.8, and 1. Usually in your homework, we give you the point. We say, find linear approximation at something. Here, I'm just telling you this is how scientists work. If they want this number, or this number, and this number, the whole idea is to find linear approximation that will be close to all of those three. And 0 seems to be close to all of those three. 0 will be close to negative 0.8, 0 is close to 1, and 0 is close to 0.17. So let's find approximation for at x equals 0. Again, usually we give you this. Usually this thing is given. But I wanted to point out that this is how science is made. Okay, I will point out, usually this is given. Then, if x is my a, so a, I'm plugging in 0 everywhere, so it becomes f at 0 plus f prime at 0 times x minus 0. And then I just need to calculate all of this, knowing that my f, let's call it not y, let's call it f of x, is sine x. So, f at 0 is sine at 0. Sine at 0 is what? 0, good job. Then f prime at 0 is, what is derivative of sine? Cosine at 0. What is cosine of 0? 1. Thus, linear approximation for this function is f of 0 at 0 plus 1 x minus 0. If you simplify all of this, it just becomes x. So it's crazy, but it's actually not crazy to say that sine of x behaves approximately like x around 0. Around x equals 0. And that's true. That's true. We actually showed you this before using limits when we showed you that a limit as sine x over x as x goes to 0 is 1. This limit actually, we saw this limit a couple times in homework. This limit actually says that sine x divided by x gives you 1 around 0 because sine x behaves like x around 0. And I prepared this picture for you. That means around 0, instead of using stupid trigonometric functions, I can use line. And line is, you know what it is? Y equals x. It's like the easiest case you can have. It's not even 5x minus pi. It's like y equals x. And instead of finding sine of 0.17, I can find x at 0.17. So what is x at 0.17? Approximately 0.17, because it's just x. This is crazy. approximately negative 0.8, and approximately 1. That's basically the answer for all of this, but only round to 0, right? Around a equals 0. And then we're gonna find how good our results are finding the error.